Okay, so let's do some examples. So what we're going to do is we're going to take this function, or we're going to use the quotient rule and the product rule, and we're going to see the differences in the two different methods. Okay, so in both methods, regardless of which way we're going to do this, we need to call one function u and one function v. It's very important so that we keep track of the order. Now we're using the quotient rule, so order matters. So if I want to differentiate with respect to x, right, using the quotient rule, I need to take v, which is 2x minus 3, and I need to multiply that by the derivative of u. So u is x cubed plus 1, so its derivative is 3x squared. Now, very important, we must subtract. This is the quotient rule, so we subtract, and then we take u, which is x cubed plus 1, and we're going to multiply that by the derivative of v. So the inside function v is just 2x minus 3, and its derivative is just 2. And we're going to divide all of this by v squared. So that's just the bottom term squared. So 2x minus 3 all squared. And we can tidy this up. Okay, there's unfortunately no nice way to tidy this up, so we just expand out. So we get 6x cubed minus 9x squared. And then we have this 2 here, so minus 2x cubed, and then minus 2 all over the denominator squared. So we can collect like terms, and so we'll get 4x cubed minus 9x squared minus 2 all over 2x minus 3 all squared. And we could continue by trying to factorize that, but we're not going to. Okay, if we wanted to use the product rule, we'd need to change the equation into y equal to x cubed plus 1 and bring this term to the numerator, so 2x minus 3 to the power of minus 1. So now we're going to use the product rule. So the order that we do this doesn't matter, but if we stick to the same order, then we won't mess it up if we're using the quotient rule. So now we want to find dy by dx using the product rule. So again, we need to name our functions. Call this one u, call this one v. So we're going to do vuv, so v is just 2x minus 3 to the power of minus 1. All right, don't forget the minus sign, it belongs to the function. Okay. And then we want times the derivative of u. So this is 3x squared. And now we're going to add, and we're going to add u, which is x cubed plus 1, and we're going to multiply by the derivative of v. Okay, so the derivative of v, we need to use the chain rule to differentiate it. It's a function in a function. Okay, I'm just going to slide this off to the left. So we're going to multiply by the power and reduce the power by 1 and multiply by the derivative of the inside function. So the inside derivative would be 2. And now I can tidy things up. So here I have this minus 1. I'm going to send it back to the denominator. So we have 3x squared all over 2x minus 3 plus 2 times x cubed plus 1 all over, minus 2 times x cubed plus 1 all over the denominator squared. Okay, and now you can actually see where the quotient rule has already done most of the hard work for us, because now what we need to do is we need to get a common denominator. So I need to multiply this first term by 2x minus 3 so that it has the same denominator, and then we'll have this minus 2x cubed minus 2. All of this is now going to be over 2x minus 3 squared. So simplifying out here, we can expand, and we're going to get 6x cubed minus 9x squared minus 2x cubed minus 2 all over the denominator squared, and you can see that that's similar to that, and we're going to get the same result. Okay, the difference being that here we needed to create a common denominator to add the two terms together. And with the quotient rule, that by virtue of us deriving the quotient rule, that's already been done for us. Okay, now depending again on the specific question at hand, it all depends on which method is going to be easier. Sometimes the product rule does work out to be easier. Let's just have a look at one more example. So here we are asked to find the derivative of these two functions, okay? And we're going to use the quotient rule, but we need to rewrite this in order to differentiate this. So this will be y equal to x plus 1 squared over, and we need to rewrite this as x plus 2 to the power of a half. So let's call one u, and we'll call the other one v. And we're going to use the quotient rule. So the quotient rule says if I'm differentiating a quotient of two functions, then I'm going to take vuv on v squared. So v u dash minus u v dash all over v squared. So let's do it. So we want the derivative. So the derivative here is going to be dy on dx. So we need to take our function v. Our function v is x plus 2 to the power of a half. And we're going to multiply that by the derivative of u. So u is a composite function, a function in a function, so we need to use the chain rule. So we multiply by the function or the power, and then we reduce the power by 1. And then we multiply by the derivative of the inside function, which in this case happens to be 1, so there's no need to write that. Now I'm going to subtract, and I'm going to take u this time, and I'm going to multiply that by the derivative of v. So v again is a composite function, it's a function in a function, so I need to use the chain rule. So I multiply by the power, and then I'm going to reduce the power by 1, so I'm going to get minus a half. And then I'm going to multiply by the derivative of the inside, which happens to be 1. And all of this is over the denominator squared. So we have x plus 2 to the power of a half all squared. Okay, so we can tidy this up a little bit by noticing that if we square the denominator, the square will disappear. Also clean the numerator up. So let's have a look at how we could do that. So here we have 2x plus 1 times x plus 2 to the power of a half, and we're subtracting. We have a half here, or another way we could write this is in terms of keeping everything positive. So on the top we're going to have x plus 1 squared, and this x plus 2 to the power of minus half is going to go to the bottom. So we're going to get 2, because that was already on the denominator, and x plus 2 to the power of a half. And all of this is still over the denominator squared, but we can just write that as x plus 2, because these are going to cancel. Well, not cancel out, they're going to multiply to become 1. Okay, now here we want to add these two terms at the top together, so I need a common denominator. So here is the denominator that I need to put both terms under, right? So I need to multiply the other term by that in order to get that result. So I'm going to take 2, x plus 1, x plus 2 to the power of a half, and I'm going to multiply it by 2, x plus 2 to the power of a half, and then I'm left with this minus x plus 1 squared, and all of this now is over 2, x plus 2 to the power of a half, which is all over x plus 2. So I can move this down, right, because I have something divided by something. I can put the denominators together, and I can tidy up the top. I'll notice that I'm multiplying two things. with the same base, so I can add their exponents, and what's going to happen is the half plus a half is going to nicely cancel out into x plus 2. So I'm going to have here 4x plus 1, x plus 2, minus x plus 1 squared all over 2 the square root of x plus 2 times x plus 2, and we can further simplify by taking this out as a common factor, and so we will be left with 4x plus 8 minus x minus 1 all over 2 square root of x plus 2 times x plus 2. And so one final bit of simplification, x plus 1, 3x plus 7 all over, right? We can use one further indices law. Here we have the same base again. The square root is to the power of a half. This is to the power of 1. And so when we multiply by two bases with this, or multiply two things with the same base, we add the exponents, and so we can write this as x plus 2 to the power of 3 over 2. So if we had to find solutions where the gradient was equal to 0, we would have to go this far in order to factorize the function. So it's good practice in the long run just to get in the hang of this. Okay, so this here is my gradient function. So the quotient rule is messy. It can be very tedious, but with lots of practice, you will get good at it.